Yeah.
All right, so we're gonna kind of dive in today, primarily into regression. So here we'll be looking at kind of week 4 materials. I know that last week they kind of touched on it a little bit. Spent a lot, basically the whole class on Tuesday looking at how we did confidence intervals, hypothesis testing, some other things in Stata. So today we'll probably do a little bit less work in Stata and kind of focus more on kind of the theoretical aspects of regression, but I'll kind of jump back and forth in between the two. We'll have an in-class quiz that we'll look at towards the end of class. And then there's going to be this second quiz. So I've had those sample questions up there. We'll probably get through everything you would need to answer every question in that quiz today. So I'll probably post it after today. It's not due until the end of the day next Thursday. So we're going to still be talking about linear regression, moving on probably to multiple linear regression on Tuesday's class. If it were me, I might start to review those sample questions, but I might hold off on taking the quiz until even after Tuesday's class. Just as we go through more examples, it's going to, just seeing more interpretations of some of these coefficients, which we'll talk about later on today, I think will be helpful. But if we do get through all of the material, I probably will post that quiz so that it is available, but it's not due until the end of the day next Thursday. Okay. So we will, and then when we do go into Stata, we've got the data files that we might be using today. I've got the do file that I'll be using. So this is something, if you haven't already downloaded these, kind of move them to your OneDrive so you can kind of access, work along with me. Other than that, we'll go pretty quickly through these first few slides, which again, the placement lecture should have went through a lot of it, but also not afraid to ask questions. Okay. All right, so basically, what are we doing with regression? Well, anytime you have a scatter plot of data, you would have a line that would best fit that data. Right? This is like you guys took 370, so this shouldn't be a crazy idea. Thinking about the scatter plot of data, you want to draw a line that kind of best fits that data. Now, ultimately, what are you interested in? You're not super interested in the intercept. You're interested in what is this relationship between your x and y variable, right? As x goes up or down, is the y variable, the y value going up or down, or is it not changing? So what we're going to do with linear regression is we write this slightly differently, right? Because the notation is the intercept we'll kind of start writing as beta subscript 0. This is where we use Greek letters a lot in stats. So beta subscript 0 will be our intercept. Beta 1 is what we're going to call our slope coefficient. So this we'll call our intercept coefficient. Beta 1 is going to be the slope coefficient associated with the first variable. Now today, won't we ever be dealing with one variable on the right-hand side here? Over time, we'll start to talk about multiple linear regression, where we can have multiple x variables. Now we got to walk through the front. This slope coefficient is going to tell us that as x goes up, how is y going to change? In fact, it has a more specific interpretation. How would I interpret beta 1 here? If x goes up by 1 unit, how many units is y going to go up or down by? That's what beta 1 is telling us. That's what that slope coefficient is telling us. Now it's simple math, right? If I'm trying to predict the y value, well, these are going to be actual numbers. So if x goes up by 1, how much would y go up by? Well, beta 1 times 2 or beta 1 times 3, they would go up by whatever beta 1 is. Right? It's just a line. Right? That's all we're doing here. So some other terms we'll use, this x variable, we're going to call the independent variable. So it's the thing that's changing on its own. The y variable is going to be our dependent variable. It changes because x is changing, right? It depends on x, okay? So if I'm looking at kind of a scatter plot of data, and I'm thinking about, all right, if I had to draw a line that kind of best fit this data, it would look something like this, right? So based off of all the data that I see, where would the line that kind of best fits that data? Now we'll talk about how we determine if it best fits the data in a second. But just for now, we can think about like visually, we kind of try to do our best, right? Well, it's going to have some intercept, right? It's going to start at some y value when x is equal to 0. Think about it here. If I was trying to predict the value for y, when x is 0, 0 times anything, I have a little typo here because this shouldn't be 0. I probably copy and pasted. It should be 1. So anytime x is 0, 0 times anything is 0, I'm going to start out at my intercept. Now, the slope of that line is going to tell me that as x goes up by 1 unit, how much is y changing by? In this case, beta 1 is actually below what value? I have a downward sloping line. Beta 1 has to be negative, right? So here I know that beta 1 can be positive, but it can also be negative if I have a downward sloping line. So, we have all kinds of relationships. If I had something like this, what's my beta 1 going to be? What's my slope coefficient? Basically 0. There's no relationship, right? What about something like this? Well, now I know it's positive, right? Now, initially, we're just going to look at linear relationships. By the end of this semester, maybe even getting into the midterm, we'll start to talk about not only can we have a linear relationship, right? We can actually have nonlinear relationships, right? So if I had to draw a line that best fits this data, if I try to draw a straight line, it's like, it's kind of good in the middle, but it's not very good here and here. I might actually want to draw a line that has some curve to it. So we can have negative linear, positive linear. We can also have positive nonlinear, and then kind of, right? Actually, this would be kind of positive nonlinear as well. We have upward sloping. It's just kind of in different rates, right? Increasing at decreasing rates or increasing at increasing rates, right? And then we could have the flip, decreasing at increasing rates, decreasing at decreasing rates. We're not going to hold off on the nonlinear stuff for a while, but kind of foreshadowing where we'll eventually get to, okay? So when I talk about this line of best fit, right? When I'm trying to come up with, when I look at the actual data, I have the actual values for X and the actual values for Y. So maybe this is something like, I don't know, I want to look at the relationship between college GPAs and starting salaries. Right? That's my X and Y variable. Okay. Well, I have the actual data set. I have actual salaries and I have actual college GPAs. But what I can do is my line of best fit is going to give me, based off of that individual's college GPA, what is their predicted starting salary? So I'm going to try to come up with, from the actual X values, what are my predicted values for Y? Okay. So when I have my line of best fit, that scatter plot of data, when I start to plug in different values for X, so I start to plug in different college GPAs, it's going to give me what, on average, the predicted starting salary would be. So it's the expected value of my Y variable given whatever value I'm plugging in for X. Now, for any one person, I mean, if I take two people, they have the same college GPA, I'm going to come up with the same predicted starting salary. When I look at the actual data, do those people have to have the same starting salary? No. In fact, in very naive regressions, there's a lot of things we're not accounting for yet, right? And so our predicted Y values might not be the same as the actual Y values. So what we want to do with this line of best fit is essentially, for every observation in our data set, because we can see the actual Y values, we can come up with a prediction for every single observation and then say, all right, how far off is our prediction? So Y hat, anytime we write hat in this class, it's going to mean this is like an estimate or this is a prediction. Okay? So we come up with these predicted Y values based off of this line of best fit, and we'll talk about where those coefficients come from in a second. And the difference between the predicted and actual Y, we're going to call that epsilon, or our error term. It looks like an E, so that kind of works out to be nice, right? But technically, the Greek letter is epsilon. And I usually just refer to it, this is our error. It's the difference between the actual and the predicted Y values. Okay? I think the book, I probably should double check this. I switched books. Usually it'll refer to it as U. We do some different stuff later on. I'm always going to kind of refer to the error term as epsilon. Honestly, for one reason, because it looks like an E and it makes it easier starting out for all of us to think about this as the error term, okay? So with this idea of we're making errors based off this line of best fit, where are these coefficients coming from? Well, if I were to just plug in different values for X, I'm always going to get the same, for every X value, I'm always going to get the same predicted Y value. So those predicted Y values are always going to be the same when I'm plugging in the same values for X, and they would essentially give me this line, right? Or what will hopefully be our line of best fit. Now, the way that we know it's our line of best fit is that if I'm looking at for every single observation, so like let's say I choose, let's do this one here. If I choose this X value, what is my predicted Y value? Right here. That's quite a bit different than the actual Y value for someone in the data set that had that value for X. So for some of these observations, my predicted Y value, given that observation's value for X, is going to be way off of the actual Y value. I'm making a pretty large error for that one data point. But now if I look across all of these, right, so that's my error just for one observation, for this one here, my error isn't quite as large. And I don't think I have a depiction here, but this one, my error is really small. I'm doing a really good job predicting this person's, I guess in my earlier example, starting salary from their GPA, right? So for every observation, we're going to be making an error. Like, we're not going to be perfectly predicting what the actual Y values are going to be. The line of best fit would be the line that, given our predictions, across every observation, we're making the smallest amount of errors across every observation, or what we would say, the sum of all of our errors is the smallest possible. So our line of best fit, let's see if I've got it in here, right, is going to be the line that minimizes the sum of our squared error terms. Okay? So when I look at the data, in fact, I said A and B here, just to be lined up with, I think I switched the notation to kind of match up with the book. I was using some old stuff. So, well, there you go. I want to show you this. So when we look across every single observation, if we were doing this by hand, what we would have to do is go through and look at this line, come up with all our predicted Y values, and then for every observation, go through, calculate the error for this observation. Calculate the error for this observation. Calculate the error for this observation. Add them all up, right? And then not only are we going to look at the error, we don't care what direction we're off by. So this would be a problem if I add up my errors. Whenever I've over-predicted, the actual Y value would be below the prediction, so I have a negative value. If I under-predicted, the actual Y value is above. Well, positives and negatives would cancel out. It could look like I'm making no errors at all. So we actually don't care what direction we're making. So we'd actually look at the absolute value of our error. Not only do we want to look at not are we above or below, we don't care. We just care that we made an error. We're not just going to look at the absolute value. We want to penalize really bad errors. So how can I penalize a really bad error? We talked about it with the variance. You calculate the variance, what do? You look at the difference from the mean and you square it, right? 1 squared is 1, 2 squared is 4, 3 squared is 9, right? So we're actually going to try to choose these coefficients that would give us our line of best fit that minimizes the sum of our errors across every observation, but not just the sum of our errors, the sum of our squared error terms. So here, I'm going to have this function that I want to try to minimize. It's the error term, right? I could rewrite that as the difference between Y, actual Y values, and my predicted Y values. The errors squared, adding them up from the first to the very last observation of my data set, that's what I want to minimize. Okay? Now, to get my predicted Y values, I know that they're going to come from this line of best fit. Now, I don't know what the intercept and slope coefficient are, right? But if I want to minimize a function, I don't know everyone's math background, how would I do that? I just have a function, let's say I'm choosing one thing. I'm trying to figure out how do I maximize this function. I take the derivative, right? And then I set it equal to 0 and I solve, right? We have two things we're choosing here. We're choosing the slope and the intercept, we're choosing the intercept and the slope coefficient, right? So I would take a derivative of this function in respect to both of those things, set it equal to 0, and then solve. I'm not going to waste your time doing the actual derivatives in math, right? It's not overly interesting. But if we do that, we would end up with this guy here, right? If we solve this, we take a derivative of both of these this function in respect to both of these slope-intercept coefficient. When we eventually solve for that slope coefficient, it would be equal to that equation, right? And you can kind of see where that's coming from. Like we've got differences in y's, x's squared. You know, the original one, we've got like a y here, but then this is squared. So, you know, just a bunch of mathematics that we don't really want to have to worry about doing. So many people have solved this. We know what the equation for that slope coefficient is. Now, we also know the equation for our intercept coefficient. It looks a little bit easier. So I'll kind of talk through these a little bit. But what does this kind of look like? I've got it written over here in terms of the notation. But if I'm looking at the sum of the deviations of the x variable from its mean times the deviation of the y variable from its mean, that was how we calculated covariances, right? Because it's not the same variable. I'm looking at the deviation of two different variables, right? So that was how. Now, what do we really technically need to have the covariance? It would be the sum of these deviations divided by our sample size, right? But if I divide both of these by my sample size, notice the numerator would become my covariance. And if I take the deviation of x from the mean squared, add them all up, if I were to divide that by n, that would give me my variance of the x variable. So this equation works out to be that this line of best fit, the equation for what that slope coefficient that will always minimize the sum of those squared errors will always be the covariance between your x and y variable divided by the variance of that x variable. Now, I'm not going to have to do this by hand every single time. State is actually just going to spit out what that value is to us because these are actual points in our data set. This is every observation. We have an x and y value, so it goes through and it computes those for us. Now, the intercept is a little bit easier. You take the average y. Once you know the slope coefficient value, you multiply that by the average x. Average y minus that slope coefficient times the average x will give you your slope, will give you your intercept coefficient. Okay? So we'll look at the actual data and kind of use these formulas, but these are always going to be the same. So this will start to lead us to, as we get closer, to the next exam, we're going to have a formula sheet. These are going to be two of the formulas that'll be some of the first formulas on there in terms of the linear regression stuff. Okay? So it looks like the numerator looks similar to our covariance. The denominator looks similar to our variance. And I'll kind of point this out as we look at some output today that prove to you that this is the case. Okay. Did he go through any of this or no? No? Okay. So I know a lot of people don't like to teach it this way, but this lines up with things that we've already talked about, and I can kind of show you here in just a second. So I think I've actually got an example here, but we'll hold off because I want to get through some of this interpretation stuff before we start working with. So we know that Stata can come up with these values for us, right? This intercept and this slope coefficient. But once we have those, we now can have this line of best fit. We know it's the line that's going to minimize the sum of our squared errors, okay? How do I interpret those values, okay? So let's say I'm looking at this equation and I run this regression, Stata spits out at me some values. Well, theta 1, we kind of think about it's how much my y value is going to increase every time the x variable goes up by 1 unit. I mean, this is basically the interpretation of a line. If you had like a y equals mx plus b, right? That slope is telling you how much y is going to change by when the x variable changes by 1. In this case, we're dealing not just with numbers, we're dealing with numbers that mean something. Dollars, people, right? Number of, certain product they have, quantities, right? So the way we'll always interpret the slope coefficient is it's the expected or predicted increase in our y variable from a 1 unit change in our x variable. Now, how would I interpret my slope coefficient? Well, this is just going to be if the x variable is equal to 0, this is the expected value of y, right? I mean, when the x variable is equal to 0, 0 times anything is 0. This is the predicted or expected value for y. Now, when we're coming up with our predictions we're only using this part of the equation. the actual Y values we see would be the prediction plus whatever error we were making. So remember, like, oh, focus this here. There we go. So if I think about the actual Y values, if I were using those kind of values that gave me that line of best fit that minimized the sum of the squared error terms, this would be how I would make my predicted Y values. But if I add in that error term, well, what was the error term? What was the difference between actual and predicted Y? If I've got Y on both sides here, when I subtract it, it would cancel. I add predicted Y over to this side. It's basically just saying, oh yeah, here is my predicted Y value. The actual Y values will be my prediction plus however far off I was, right? However much the error I was making. So just different ways of kind of saying the same thing there. But when we're making our actual predictions, we don't use the error, right? We're just using those estimates that gave us our line of best fit. Okay. Questions before we keep moving there? Like I said, I'm moving through this stuff a little bit quicker, hopefully to kind of spend some time on some things I think are a little trickier, right? So I had this data set. I'll kind of show you some output from Stata that I was using. So I had income and I had the number of days someone smoked marijuana each month. I don't remember where I found this data set, but I had a lot of observations, right? 5,000. The average income, it was kind of older data. So the average income was like 28,000. I also think, if I remember right, it was something like, I think this was predominantly like, this was in some college. It didn't say what town. It was like, it's a college town in the Pacific Northwest or something. So I don't know exactly where it was at. So pretty low. And then kind of, we had the median number of days used 0. So there's a lot of people that don't use it all, but then we had some variation in that variable. So I just looked at 1 year of data because I thought maybe over time this starts to look different. So I used kind of 2010. I ran this regression. So we'll look at Stata in a second how we run these regressions, but basically the very simple linear regression I wanted to estimate and come up with a slope and intercept coefficient for was, as that number of days someone uses marijuana each month changes, how much would their predicted income change by? So how would I interpret beta 1 here? Well, I run this regression. Stata gives me a bunch of stuff, right? The coefficients that I want that minimize the sum of those squared errors are negative 253. And then here, Stata will refer to the intercept as the constant. So it kind of depends on, what program you're using, or even if you look at a more statistic heavy versus economic textbook, constant or intercept are kind of interchangeable terms, right? It's the thing that's always the same, no matter what X is, right? So how would I interpret my constant here, or my intercept coefficient? So it would be the predicted Y variable. So what was I trying to predict? Y is always on my left-hand side, just like if any line, Y is equal to MX plus P, right? So it's the predicted income of an individual what? So I said it's the predicted value of Y, and our X variable is equal to
0.
0. So for someone who uses marijuana 0 days a month, their predicted income would be about 32,000. 32,149 to be exact, right? Now, from this data set, right, how would I interpret my slope coefficient? So we said the slope coefficient, the general way we interpret it is it's a 1 unit change in my X variable. We'll change the predicted Y variable by whatever that slope coefficient is. So what's a 1 unit change in my X variable here? Someone who uses marijuana
1 day is minus 253.
one more day a month. We would expect their income is 253. How do we measure income? Dollars lower, right? So when we start to look at these variables, we're going to make the interpretation using their specific units. I had someone in one of my B251 classes ask me, what's the difference between economic and financial consulting? Economic consulting, we're not as kind of, I think financial consulting, I told them, it's like you're just looking at the numbers and you're just looking at what your models are predicting in terms of your plugging and chugging. economics should hopefully give you a little bit more insight, even if you don't have data to back it up. You can kind of know the principles that apply with these things. Same way, I think, even when we're dealing with data, the real advantage of being like an economics major, have an economic kind of view of it, is you don't get as lost in the numbers, and you want to get more involved in the interpretation of what those numbers are telling you. And so for us, units and things really matter, right? That's the value of being able to kind of understand these relationships, is not just like X is telling me Y, it's okay, what are X and Y, right? And how am I applying this to like real world examples where it's not just two random X and Y variables, it's things that actually have meaning in the real world. So we've got the number of days someone's using a specific drug and their income in terms of dollars, right? So that's just how we make these interpretations, okay? So, interpreting these coefficients, we kind of just walk through that. I don't think it's too terribly tough, right? So we had that interpretation of our slope coefficient, and I even threw in how we interpreted that slope coefficient as well. Slope coefficient, and then how we interpreted that intercept coefficient as well. Okay. And this is where I must have been copying and pasting like a fiend, because this is definitely right. This was our intercept coefficient interpretation. Okay. Is there anything else I want to say here? I think I've got R squared stuff here. We'll go through one more example, and then we'll kind of hop over to stata. So this is kind of just what I said in words. Let's say I wanted to estimate the following regression. Okay. So I had some COVID data laying around, and I was looking at county level data. So this was the percent of the county that was vaccinated, and this was the number of cases that county saw per 1,000 people. Okay. So, I might be interested, okay, if they were getting a higher percent of their county vaccinated, what should I expect the sign of beta 1 to be? Vaccine's working, because I get more people vaccinated. I expect that there's fewer cases, right? So, Fauci's probably loving my results here, right? So as I saw how would my X variable be measured? It's percent. So what's a 1 unit increase? If I got 1% more of my county vaccinated, the expected decrease in the number of cases per 1,000 people is 0.25. That might not sound like a very large, but that's per 1,000 people. I mean, some counties have millions, right? And then so, I would just scale that up to however large the county was. But this is telling me what that relationship was between percent vaccinated and the number of expected cases per 1,000 people I would see. Now, how would I interpret my constant or my intercept?
Nobody got vaccinated. How many?
If nobody got vaccinated, the expected number of cases per 1,000 people would be about 51-ish, right? So this is kind of how we make these interpretations. Now, I'm being very naive. These simple linear regressions, we're ignoring a lot of other factors. But we've got to walk before we can run. So we're just trying to understand these simple linear regressions before we talk about how do we control for those other factors, okay? So up this point, I just kind of want to focus on the interpretation of these, kind of getting used to interpreting this. One more thing we'll talk about kind of before. So the next thing that I want to talk about before we jump into stata is, okay, so I have this estimate for what this relationship is, but is the percent of a county that's vaccinated, is it explaining, like, is it a good predictor? I know that I can use it as a predictor, but is it a good predictor of the number of cases I'm seeing? So what we're going to want to look at to determine this question is another statistic that stata is telling us here, which is going to be this R squared. Okay. So R squared, you touch on this last week at all? No. So the R squared, and what did he do? No, I'm just, so the R squared, that was me not talking, okay? I'll come back to this, but I do want to kind of touch on the R squared here. So what the R squared is telling us is when I look at a Y variable, there's going to be a certain amount of variation that exists, right? Just in the data itself. And I want to know, okay, this one X variable that I use to try to predict it, how much of the variation in Y am I explaining with this one variable? So in our example back here, how much of the variation that exists in the number of COVID cases? So if I just looked at the variance of the number of COVID cases, how much of that variation can I explain just with the percent of the county that's vaccinated? Okay. So if I'm looking here, my R squared was 0.04. So the way that Stata shows us the R squared, the way that Stata is going to show us anything that we eventually talk about as a percent is everything's in like proportions. So if I have 0.04, if I want to convert that into a percentage, so this is saying the percent of a county that's vaccinated, the proportion of the variation in that number of COVID cases, the Y variable, it's explaining 0.04. That's the proportion it can explain. So the percent it's explaining would be, how do I go from a proportion to a percent? Just multiply by 100, so 4.2%. So I'm really only explaining about 4.2% of the variation in the number of COVID cases using the percent of the county that was vaccinated. So what's true? There's a lot of other things that would be better predictors at how many COVID cases I see in a county other than just the percent that's vaccinated, right? So where this kind of comes from is what we would do is we'll say, okay, look, there is some total sum of squares. Now, what should this look pretty similar to? If I take Y, I subtract the average, I square that deviation from the mean, add them up across every observation, that's really close to my variance. The only thing I'm missing is I would need to divide by my sample size or sample size -1 if it's sample data instead of population data. So our denominator here, really this total sum of squares, it's essentially the variance that exists in that Y variable. It's really the same thing, okay? Now, the explained sum of squares would be if I just took my predicted Y values and their deviations from the mean, square them and add them all up, how much variation in those predictions would I see? And then what proportion of the variation, my predictions, like kind of that relative to the total variation in the actual Y values. The actual Y values will include my prediction plus what? I said the actual Y values will be my prediction, but also this error that we're making, right? So this would include all of the variation in Y. Here is just the variation in Y that my predictions are explaining, okay? And that's why we can interpret the R squared as the proportion of the variation in Y, our one variable we were using to predict Y, is explained. And then we scaled it up to a percentage by multiplying it by 100, right? So if I looked at an example like this, I always try to like find these weird data sets of things that people talk about and then be like, yeah, I don't know. The data doesn't seem to necessarily support it a whole lot. So have you ever heard of shale wells, oil shale wells? So it's like a way of like mining oil and like supposedly it's terrible for the drinking water in the nearby area. I am no geologist. This is just my very base level understanding. So I have on this data set and it had total shale wells. And I believe once again, this must have been county level data. Probably didn't have all the counties. It was probably a specific area of the country. Well, that makes sense. Not every county you're going to see oil shale wells. So this is just probably the counties that had oil shale wells in them. And I had the number of births I was trying to predict. So the idea is that if these oil shale, like these wells are bad and you're getting in the drinking water, it's actually going to cause the birth rates to go down. It's going to cause more miscarriages. It's going to prevent pregnancies. And so we run this regression and say, oh, sure enough, how would I interpret my slope coefficient here? If I see one more of these wells in a county, the predicted number of births is going to go down by 3.9. So there's some kind of a correlation here at the very least. And then how would I interpret my intercept? If a county had no wells, their expected birth rate would be about 6,100. Okay. Now, if I'm looking at my R squared here, is this a good predictor of the number of births? Or is this explaining a lot of the variation that I see in the number of births? My R squared is what? 0. I mean, it's something above 0, but it's so low that to the fourth decimal, it doesn't register. So essentially, how much of the variation in births am I explaining with the number of oil shale wells in the county? Almost nothing, right? If I'm trying to predict births, I need to go find better variables, right? This is not a very good predictor, okay? So that's how we want to kind of think about interpreting or thinking about our R squared here. Now, all of these coefficients, well, if I have this here, I don't want to jump too much. We're around time. Okay. We'll do one more R squared example, and then I want to jump to state again. So I've got a second example. So I'm going back to the vaccinated variable. Right? So we said we had kind of 4.2% was our R squared there. I can think about if I like left that out, where is it coming up with that value? I said it's going to be the total variation that exists in my Y variable. So when I'm looking at kind of this SS column, so I said it was like the explained sum of squares. So this is the variation my prediction was explaining. Total sum of squares was the total variation that existed in the variable itself. Those values are also reported to us in Stata, right? So in fact, if I take my model's sum of squares, so this is the sum of the squared errors that my model explains, right? So Stata sometimes is a little bit different than how we will kind of see the notation or how we see this written statistically. But the model sum of squares is the same as our explained sum of squares. So if I take that value and divide it by my total sum of squares, that should reproduce for me my R squared value. So if I take my explained sum of squares divided by my total, sure enough, I end up getting that R squared. So a lot of the times, even though I'm getting a lot of this data or this output from Stata, it's just doing a bunch of math behind the scenes, right? And we probably won't focus as much on these values, but down the road, in fact, we will use them a little bit later on this semester to do some other things. And so I want to mention here, like, we're not just having all of this for the sake of having all of this in front of us. It's going to be useful for things that we're going to do later on. For now, right, probably the types of questions you're going to see are primarily just going to focus on that R squared. But when we start to talk about things like this adjusted R squared, which we're not yet, that's where we might have to go back and use the components that we were using to calculate R squared and maybe do some kind of additional math, okay? So we already looked at this example in terms of interpreting that R squared. I'm gonna leave this blank because what I want to do next is think about opening up the do file for the week, which is in this folder. So we've got regression in class F25. It should be right here. And that's the do file that I'm going to be using if you want to work along. I believe that the data I'm going to open up is going to be initially this birth data and fracking. So this is like kind of the oil shale well. I've got my global path, which is actually going to be not this. Open this up. I've got my birth data. I'm going to open that up. I'm going to copy my file path. I changed it, put it in the week 4 materials. So this is where you can open it up first, or I said, always keep yours the same. I like to have these in different folders and make it harder on myself. But this is where you would paste your kind of path wherever you put that birth data file, right? So mine is in my OneDrive, your ECON 371, week 4 materials. So now if I highlight this global path, and I hit kind of that use command, it'll open it up as long as you kind of put your file path in there correctly. Once again, if it were me, maybe to make it easier, just throw every data file for this class in the same folder on your iDrive. That way, every class, your path is the same thing. But once you have that opened up, now you can kind of start working along with me. Or if you just want to drag it over and open the birth data, that's also fine. So we can start out, right? We kind of have this scatter plot. So this was like our first problem set. We already kind of looked at this previously, but I have the actual kind of Stata commands that would create this scatter plot for me. We said that I also could kind of go to Where is it? Now I'm gonna forget where it's at because I don't remember the code. So this will be what, data. There it is, graphics. I go to a two-way graph. I can create of my scatter plot doing it this way. Once we know what the command is, right, I can always just kind of use that same two-way scatter command and then just put whatever two variables I want to know relation between. So here I've got the number of births and then kind of the number of oil shale wells in that count. Okay. Now, this is where, you know, sometimes it's kind of tricky. If I was to draw a line that best fit this data, I don't know. Right? If I had to draw just a linear curve that best fit this, it's pretty steep, but I know I'm going to be making quite a bit of errors. It's kind of hard to like really draw in a line of best fit. But if we have the data, we can estimate what that line of best fit would be, and we don't have to worry about like eyeballing it, right? We can come up with the actual values that would give us the line that minimizes some of the squared errors. So I'm going to actually run this regression command. So all you have to do, and this one, it's definitely easier. You could go up here and go to Stata, linear regression. You can select your dependent variable. Remember, our dependent variable is going to be what we're trying to predict, or what our Y variable is on the left-hand side. So I could find that it's the number of births. I could select my independent variable, which is number of wells. I've got other options, which we haven't talked about, so I'm not going to worry about those. I can hit OK, and it'll run my regression for me. Or anytime I'm running a regression from here for the rest of the semester, the command is just reg. And then what is my Y variable goes first, and what is my X variable? That's what goes second. Okay. So all of these things that I give you these commands for, there is a way to do them from like the user-friendly interface. Like you just saw when I opened up like stats, there was like 30 different things, categories, and I have to like hunt for them. So I'm always going to give you the commands that you need in these do files. So if I were me, instead of trying to use the interface, I'd start to try to get used to like just kind of copy and pasting, right? Or sorry, copy and pasting. Trying to mimic what I'm doing in these do files. What comes first? That's my Y variable. What comes second? That's my X variable. And I try to add in comments here that remind you, like, this is the line of best fit we're trying to estimate, right? Here's my Y variable is the number of births. Here's my X variable, the number of wells, or these oil wells. So I can do different things. So maybe when I run this regression, I look at this output, and it actually looks a little bit different than what I showed you in class because I'm using all the data here, and the R squared is basically 0. Right? But when I was looking at that scatter plot, so this is where I can always kind of go back and rerun. Notice there's a lot of counties with zeros, right? So I don't know. It might be that there's so many counties with zeros, it's kind of skewing my data a little bit. So I might want to just, okay, let's look at every single county that has at least one of these wells. So I want to run that same regression, but only if I want to run, so like we did conditional means, I only want to run this regression conditional on if the observation has at least one well. And then I want to know, okay, as it has more of these wells, now I'm only looking at counties that at least have one. Now I might be getting a little more accurate of an idea about how destructive these wells might be on different biological markers. Here, we're just looking at the number of births. So I can add in conditional statements just as a reminder. If we ever want to do not equals to, that's a exclamation point, right? That's not equal. So not is kind of the explanation point or exclamation point. So I could run that same regression. Notice now instead of 170 observations, oh, only 22 of these actually had at least one well. So I might have, very different results. Sure enough, if I'm only looking at the counties that have these, now having one more well actually looks like it's not quite as detrimental as I thought before, right? The size of that slope coefficient is not quite, cut in half, but close, right? I was up close to -4. Now I'm closer to about -2. So when we run these conditional regressions, we might get very different results. And that's because we're using a different data set to estimate this slope and intercept coefficient. Okay. Now, we still have a R squared that's basically 0, so I would still probably think this might not be the best predictor of the number of births, but we're just looking at a data set here, kind of running through some stuff. So what I wanted to kind of give you some support for was I told you that very early on, we were looking at like taking the derivative of that sum of the squared errors and minimizing. I said it looks like that slope coefficient is the covariance of that x and y variable divided by the variance of your x variable. So in this case, it should be, I can find the covariance between the number of births and these oil wells. I can then find the variance of my x variable, the number of oil wells, and hopefully that ratio should give me that same kind of coefficient I was finding of negative 3.92 before I did the condition, right? I'm now looking back at the unconditional results. So when I run this regression and I get that slope coefficient of negative 3.92, if I use my sum comma detail, this will give me my variance. So once again, when we're thinking about the problem set that's due today, and I've tried to mention this to you and people are still coming to me with questions, start working on these problem sets when I assign them early on, even though you can't do every question, especially for this first one. I tried to reiterate, I know it's tricky kind of getting used to using this program, right? But we want to, get all that out of the way so you can actually answer the questions. So here, if I were writing this out as a problem set, I have my command, but then maybe I was asked a question. In the comments, I'll put what the variance actually is, because that's what I want here. I want the variance of that x variable. That's what was in. Where's it at? There we go. That's what I said we can kind of think about as the denominator when calculating that slope coefficient. Okay. So I'll summarize my x variable, which was the number of wells. I look here, my variance is 77.48. So write that down. Okay. I then look at the covariance. So we had that. We said we could use the correlate command and then comma covariance here. There was also a way to do it kind of from the statistics, the kind of user-friendly way. But I had this already in even the last do file. I'm having it here so I can look at, okay, what's that covariance? It's negative 303.801. If I take 303.8 divided by 77, and you can verify this, or I can pull open Excel if you don't believe me, right? But you take that ratio of the covariance, 801, to the variance of my x variable, I get 3.92. I left off my negative sign there, but hopefully I'm just trying to show you that this is what it computes to, right? We get the same exact thing if I take that ratio of the covariance to the variance of my x variable as we were finding from our regression analysis for that slope coefficient. So that should always be the case when we're looking at these simple linear regressions. The slope coefficient I see should just be the covariance of that x and y variable divided by the variance of the x variable, okay? And once again, you could prove this to yourself using any data set. Should always be the case. And you could do that kind of like I did here, okay? With commands that we've already talked about, comparing that now to a new command where we're running the regression, okay? Any questions from that before we keep moving here? Okay. So this is where, instead of going to file open every single time, it's kind of nice to use that file path, because if I've set it correctly now, when I switch data sets in the middle of class, as long as I have the files downloaded in my OneDrive, as long as they're in that same place, now when I run this command, it should open up my COVID County data. Sure enough, if I then go to look at the data with the little magnifying glass browser, I've now got a new data set opened up. So we're switching data sets here to look at the other kind of results I was showing you in the slides. So the program, pull up my do file. So I can kind of do this simple linear regression. This is the one that I was showing you in class earlier. It was just predicting the number of cases. The first variable, that's my y variable. Second variable is my x variable, right? The percent that was vaccinated. I get that slope coefficient of negative 0.25 that we were looking at. Now we said what percent of the variation in the number of cases was explained by the percent that was vaccinated, only about 4.2%. That was our R squared was 0.042. We said that's always in terms of a proportion. So I want to talk about it in terms of a percentage, it's going to be 4.2%. Okay. Now let's say instead, I come down here and I want to look at this regression. So I didn't show you this yet, but this is kind of a weird example where sometimes our intercepts start to have really weird interpretations, but that's still how we're going to interpret them. Okay. So notice I looked at a specific variable here, which was like the number of cases in 1 month. And that's just because I wanted to make sure I had an example that looked kind of weird for you guys. So if I'm trying to predict the number of cases that a county had in COVID October 2021, and I'm trying to use their population with the idea in mind that larger populations, more people in the same physical area should have increased the spread of a disease, I would expect this coefficient to be positive. Having one additional person, I would expect that increases the number of cases per people, right? Because it's just giving me a more densely populated area. Sure enough, I find this positive coefficient, okay? Now, how would I interpret this coefficient? So if I remember right, the number of cases was like per person. So having one more person in my county increase the number of cases per person in my county by 0.1. So, you know, what's the economic significance of this? I mean, having one more person meant that like it was kind of increasing the spread. You know, not every person you have is going to have one more person have it. I would need essentially what? So this is the increase in the number of cases for every additional person. How would I get about one more case of COVID? Every one person adds 0.1. I would need about 10 people, right? So I can always scale up these coefficients to have different economic kind of significance, right? It's just increase the magnitude. So it always tells me the effect of one unit. I can always just scale that up to however many units I'm interested in. If I had 50 more people in my county, I would just take that coefficient and multiply it by 50, right? So I can always scale these up, right? Now, the intercept is the thing that we're going to be saying. Sometimes we'll have a weird interpretation here. So how do we interpret the intercept? It's the predicted Y value when the X variable is equal to 0. So the predicted number of cases is -6. How do I have negative COVID cases? Shouldn't the lowest COVID case I could see is 0? Well, let's think about it. I would see -16 when the population in a county was 0. Do I ever have a county that has 0? No. So what can end up happening, and it's still how we're going to interpret that intercept coefficient. The reason why that can happen is because if I'm thinking about something like my X variable is population, and I've got COVID cases was the Y variable I'm trying to predict, most of my data, my population is going to start out here, right? So let's say that even it was like a really clear relationship. These are like all data points. I'm just doing it very quick. Where's my line of best fit? Here. Where's my intercept? It's negative, but that's because I never see counties that even have populations, not just at 0, I don't even see populations below whatever this value is, right? So sometimes we can end up with these weird interpretations for our intercept, but that's just because mathematically a line has to start somewhere. So even if we will never see 0, the value in our data set for the population, that's still how we're going to interpret that slope. Sorry, not the slope, that intercept coefficient. Okay. Does that make sense what I'm saying there? So sometimes that intercept will just kind of have some weird interpretations, but that's still how we're going to interpret it. Now, the other thing that I wanted to kind of take a look at here, and excuse me, is you can always scale variables and it'll kind of make your interpretations a little bit different. So let's say I wanted to predict the number of cases I had, what, per 1,000 people here, but I want to use income to predict that. So maybe I thought like in wealthier areas, maybe they're able to like do things where they can kind of avoid, I don't know, they had the luxury of not having to go to work, or, you know, whatever the story is there. So I'm going to run this regression where I'm looking at the number of cases per 1,000 people as my Y variable, my X variable is income. So I run this regression, and sure enough, it looks like when the county actually had a higher average income, the number of expected cases was lower. Now, this is the effect of what? 1 unit for income. So this is if they had on average $1 higher of average income. So we would expect that coefficient to be very small. I can scale it up. Maybe I'm thinking like, okay, what if I wanted to say, what if the average income of that county went up by 1,000? Well, what should the effect be? If this is the effect of $1, the effect of 1,000 additional dollars would be this times 1,000. So it should be what? 1, 2, 3. Wait, negative 0.4. So I can scale it up that way, or, right, if I'm showing this, right, ultimately, like when you go out and you try to use what we're talking about in this class, hopefully you'd be like trying to use this data and show it to someone else, right? So data display is like probably a whole class in and of itself, but like this number, what does that really mean? It looks really small. They might just, who cares? Well, that's because that's $1 more. It's very likely we could look at different counties and see the average income be $1,000 higher. So what I'm going to do is create this new variable. So once again, eGen is using built-in functions. Anytime I just want to do math, addition, subtraction, division, create new variables, I just have to use gen. So I'm creating this new variable, which is the original income, but now I'm going to divide it by 1,000. So now the units of this variable, a 1 unit change will not be a $1 change. It will be a $1,000 change. So if I have this new variable and I run that same regression, but I'm using the variable I've scaled, now the coefficient I see on income, household income, should be not the effect of $1 more on average in a county, but the effect of the average income going up by 1,000. Okay. So hopefully what I'm telling you is true. Should end up seeing, sure enough, it's negative 0.4. Now, there's obviously values after that, but like, right, we're going from negative 0.0004 using the new scaled variable. This is a lot, prettier. I guess it may signal that there's an actual, looks a little bit larger. It might be better to kind of display that to a group that you're trying to convince that there's some relationship between income and the number of COVID cases. Not only that, when we were looking at that R squared earlier, I think it was like 4.2% for the number of, when we looked at vaccination. Notice what's happened to my R squared when I scaled the variable. If I'm just scaling it, have I added any new information here? No. So what's happening? When I use the original income variable, my R squared was about what, 0.11 or 11% of the variation in the number of cases I could explain with just the income of a county. When I scale the variable, should that change? No. Sure enough, still about 0.11, right? Now, also, if I'm comparing this income here, would I say that's a better or worse predictor than the percent vaccinated? Well, the percent vaccinated, I was only explaining what? 4.2%. With income, I'm explaining almost 11. Income is explaining more of the variation I see in the number of COVID cases than the percent of the county that was vaccinated, right? It's the data, right? I'm not making this up, right? And so maybe if I'm concerned with the spread of COVID, maybe I shouldn't have been worried about getting people vaccinated. Maybe I should have been more worried about giving people money so that they could do certain activities to avoid probably being around more people, right? i.e. giving people money for maybe, not having to kind of go into work. But I'm not a politician and I don't make these decisions. So, but these are the kinds of questions we can start to think about from very simple regressions here. We're not doing anything crazy yet, right? In fact, here, if I were to look at the population and I wanted to look at the cases, and actually I could probably even change this so that we're using the same variable here. But, even the population, like I would expect this would have a high R squared. It's really not as high as I would necessarily expect. So it looks like income was, you would think more people would really impact the number of cases we were seeing just because having more people in a condensed area. And that does have an effect. But back here, it's slightly negative in anytime we see this, we won't try to trick you too much with this, but we'll start getting somewhere. E to the negative basically means move that decimal 6 places to the left. Now, this is because it's the effect of one person. We'd probably want to scale that variable up, but the R squared is telling us that population explains less of the variation in the number of COVID cases even than income. If I'm looking for solutions, I'm like, what's this tie? What's this relationship of income to the number of COVID cases? There's something going on here we need to explore, right? And that's just looking at one statistic right now, which is the R squared, right? And that's kind of a good first look at it. Okay. All right. Is there anything else I want to do here? So we've got 15 minutes left. We'll do this if we have time, because I want to make sure that we get through this and have some time for it. So this should pop up now. Oh, I guess I better change the detail. Well, I'll change it here real quick. Give me a second here. So it should show up under kind of this week 4. Let me edit this real quick because I originally had planned to do this last class and we didn't get to it. So let me change that due date. All right. So it's under the quizzes, but it's also under the home tab. If you scroll down under the module 4, or not module, sorry, week 4, I'm going to go to build. You'll see the actual quiz. I'm going to go to preview so we can take a look at this. Okay. So let's say I had a regression that looks something like this, right? So I had this data set and it had high school students and they had their college GPA. So I want to try to predict what their college GPA, maybe I'm like in an admissions department at a university, and I'm trying to predict college GPA based off of the size of the high school student went. Maybe larger high schools, they have more resources available to these students. They might be more successful at the collegiate level, okay? So I'm looking at this, how would I interpret? And I'm telling you here, the high school size variable is in hundreds. Okay? So a school of 200, their class size, every grade level is 200, that would be a value of 2. So how would I interpret my slope coefficient here, beta 1, on high school size? For every 1 unit change in high school size, so what would a 1 unit change be? For every additional 100 students, the predicted college GPA would do what? Go down by about 0.01. So for every additional 100 students, my predicted GPA is going to decrease by about 0.01. So some of these I'm kind of writing like in the reverse, like for every 1 point increase in GPA, the thing that's changing is what's on the right-hand side of your regression or that X variable. So it's a 1 unit change in high school size, which was 100 additional students. And the impact it was having on my Y variable is whatever that coefficient is. So that one shouldn't be too bad. Any questions on that? All right, so same regression. This is something we didn't talk about today, but it'll kind of lead us into next class, okay? So I'm giving you the answers today, so I'm not going to try to give you the wrong. So I'll talk a lot more about this on Tuesday's class. But when I'm looking at this regression output, I haven't talked about anything that comes past the coefficient yet. Okay? So I wanted to focus on interpreting these, thinking about the R squared. There's also something else in addition to the R squared that will tell me whether or not this is a good predicting variable, whether or not this X variable is good at predicting Y. So remember, anytime we have a sample statistic, we have the sample mean. We said we could take 1,000 different samples and there's going to be a distribution. So even when I'm coming up with an estimate for these slope and intercept coefficients, this is just one sample slope coefficient. You can think about it that way. If I were to come up with a bunch of different data sets and run a bunch of different samples, I would have a distribution to these slope coefficients as well, just like my sample mean. Okay? So maybe one way of thinking about this, just to kind of give you a visual here real quick. So just like we said, our sample means we're normally distributed as long as we had a sample size over 30. around whatever that true population mean was. We've just got a different sample statistic. Our new sample statistic is an estimate for what this slope coefficient is. It's also going to be normally distributed around whatever the true population. Now, we don't know what this is. In fact, in almost no case will we ever be able to get population data to estimate what that true population coefficient is. The best we can do is come up with a sample coefficient, and we likely only have one data set. So we have to rely on what we know about statistics to say, okay, what we're always going to start out assuming is this slope coefficient is 0. We stack the deck against ourselves. We assume there's no relationship between these two variables. We then know at different levels of confidence, we can come up with critical values. What's probably easier is once I have my slope coefficient, remember, how do we come up with a test statistic for a sample mean? We took the sample mean, subtracted the true mean. Now, this wasn't the true mean here. Remember, we started to do, okay, what was the assumed true mean, right? And then we divided by standard deviation of the sample statistic we were looking at. We're going to do the same thing here. What is the assumed true value that we have for the slope coefficient? 0, right? So we actually can kind of almost ignore that. Now we divide by, you can think of it, it's kind of like the standard deviation of the slope coefficient. We have a fancier name for it, which is just the standard error, okay? But really, it's still a measure of the variation that exists in these slope coefficients, okay? So we're doing the same thing as we were doing with sample means. We'll come up with a test statistic. How would I then find my p-value? Well, what type of test, if I'm assuming this is equal to 0, I always have a two-tailed test. So I will always find the area that's more extreme than my test statistic and then multiply it by 2. Now I've got my p-value. I can just compare that to my benchmark values of 90, 95, 99%, which are alphas of 0.1, 0.05, and 0.01. So if I go back and look at this output, right, what levels would I say that high school size has predictive power for this GPA? Or what significance levels would I say that it has no predictive power? So here, I've got my coefficient estimate. This is kind of like my sample mean. Here is that standard deviation, right, for that slope coefficient, or what we call our standard error. It's just a fancier word for it. It means essentially the same thing. It comes up with our test statistic. So if what I was telling you is true, our test statistic is simply that coefficient divided by our standard error. So 0.0108 divided by 0.00589 should give us that 1.84. And I ignore the negative sign there, but if we have a negative sign, obviously we have to use that. It then looks it up in the student T table. It correctly identified what student T distribution to use. It doesn't even have to use the standard normal approximation. It then uses that p-value, and now I can start to make rejection decisions. So can I reject the null hypothesis at the 10% level? Sorry, not 10%, at the 90% level. Well, at the 90% level, what would my alpha be? 0.1, so the remaining would be 10%. So is my p-value less than 0.1? Yes, so I can reject the null. Remember, the null is that there's no relationship, or that high school size has no predictive power. So at the 90% confidence level, I can reject that null and say, no, high school size does have predictive power about someone's college GPA. Now, could I say that at the 95% confidence level? Well, my alpha there would be 0.05. Is my p-value less than that alpha? Not quite. 0.6 is just barely above 0.05, or not barely, but it is above 0.05. So I can only reject the null at that 90% level, or with 90% confidence, I can say high school size does have a relationship with college GPA. But at the 95, and then if I can't say it with 95% confidence, I definitely can't say it with 99. What would the alpha be for 99? 0.01, 0.06 is, it's not less than 0.05. It can't be less than 0.01. So the only level I can actually say I have predictive power would be that 10% level, right? Or the only level I can reject that there is no predictive power is at that kind of 10% significance level. So this is where I've kind of up to this point, we've talked a lot about confidence levels. So 90, 95, 99% confidence. When we're starting to talk about significance levels, it's just the inverse of that. So it's whatever would get us up to 100%. And when you look at like academic papers, I don't even know where this started. They often don't talk about things in terms of like confidence levels. They talk about them in terms of significance levels. So if you look at the bottom, we'll start looking at some like PDFs and things, and I'll show you at the bottom of every table. They never report the confidence levels usually. They always report the significance levels. So I can reject the null with 90% confidence, or we would say I can reject it at the 10% significance level. So again, why that is there's some statistical support behind that. I've always thought if you're trying to get your information out to a general population, it always to me made more sense. Like if I go up to somebody who's never taken a stats class and I start saying, I can tell you this with 10% significance, they're gonna be like, that's not very high. If I tell them I can tell that with 90% confidence, they're like, oh, that's pretty good. So I don't know why that's the way we do it, but that is kind of the way that you see it done in academic papers, right? So that should be kind of it for that one. And then we've got what? If we take a sample size, we have a larger sample is going to be more or less likely we reject a null. We'll hit on this a little bit more on Tuesday as well. Just like the sample mean, we said, if I've got a larger sample size, we're looking at like a standard deviation. Right? We said it was like the deviation of y from the mean squared over n, or if we had a sample n minus 1. So what was happening when we kind of took larger samples? What was happening to our distribution?
Getting narrower.
Yeah, so we can think about it this way as well. If this is getting larger, what's happening to that standard deviation? It's going down. If this is going down, seeing the same sample mean, my test statistic is going to be higher, which means my p-value is going to be lower. Is it easier to reject something when my p-value is lower? Yeah, it's more likely it's going to be less than those alpha values. Same thing applies here. Behind the scenes of this standard error, there's a sample size. So as I increase that sample size, it increases my standard error. Seeing the same estimate for my slope coefficient would produce a higher test statistic. A higher test statistic produces a lower p-value, making it more likely I can reject the null. So just like with sample means, having larger sample sizes should make it more likely we can reject that null hypothesis. Right? So we had more likely, I think the very first one was the one that we had here.
I thought this says number of observations is 4,137. So why is it more?
I think I was just giving you I said approximate here, and I was just saying if we had more. You're saying why doesn't it match up with this?
Well, I don't see how it's like the sample size is bigger.
So I'm trying to make, so I just said the sample size we had before was approximately 4,100.
Okay.
It's not, it's a little bit higher. I'm just saying if you had a large, I was just using it as a reference. So if it makes it easier, oh, sorry, I didn't switch both of them. If it makes it easier, think about this thing. If you had a larger sample, if you had 1,000 larger sample size, I was just, yeah. No, like I said, I got a little late there. So you should kind of have everything you need here. Get that submitted here in the next minute. Well, I will release that quiz once again. We'll kind of touch more on some things that are probably could answer up to this point. We're going to go over them again on Tuesday. So I would probably wait and take that until after Tuesday's class, but I will kind of have it show up there on Canvas if you did really want to take it. Okay. All right. Other than that, you have any last minute questions? I can try to answer a few after class here about that problem set. Have a fun, safe weekend, and I will see you guys on Tuesday. Thank you. All right. This here real quick.